so for those two defects, surface versus surface roughness defect versus the double hull, whatever that effect.
Yeah.
So let's say if you insert insulating, the very thin insulating layer versus, let's say, it's a metallic layer, non-magnetic metallic layer between the two.
Yes.
Then
that's what we want to do, exactly.
So if it is surface scattering, then you have to have direct contact with surface scattering method. Does not, so if you have, whether it's metal versus insulator, probably your effect will completely disappear if it is surface scattering effect, because you have to have direct contact with the magnetization versus. Well, so what do you think will be the difference if you insert metallic versus some thin insulator between, in order to tell the difference?
Yeah, I think a small non-magnetic spacer is probably required to suppress the proximity effect. Okay, so
not the proximity.
No. I understand what you mean. You know. So, but I'm saying the situation is difficult because on one hand we want some spacer to remove the possibility of proximization, right? On the other hand, you are pointing out that if we do that, then the interfacial scattering might become less spin dependent, right? That's what worries you, because yeah. So that's a trade-off. Yeah, I guess I don't know the answer in detail, but I would imagine if this spacer becomes too big, too large, then it would kill not only the proximity effect, but also our effect inevitably, right? Because you wouldn't. So the challenge is to make it big enough to avoid proximity, but not so large that this spin-dependent reflection is here. If that cannot be done, then it will not work. Okay.
Yeah. All right. Okay. So, question in the back first.
Regarding to the anomalous Hall effect in the metal insulator system, many experimental results show that anomalous Hall voltage or resistivity change with temperature, and even change sign with temperature. Does your mechanism take into account that?
Yeah, no, we don't address that. Okay, so in this theory, the spin-Hall effect, the spin-Hall angle is treated as a parameter given by, probably more reliably given by experimentalists. So yeah, I'm aware of the fact that there can be changes in sign with temperature, but that's what would all be taken into account, right? If you see the structure of the formula is such that it would reflect the change of sign. So that would be very interesting, in fact, because if the effect is linear in theta, then you would correlate, change in anomalous Hall effect with the other observed change in sign, right?
Okay, last question.
I have a question about the torque generated by surface scattering. It is believed in general that the inverse Einstein effects only contribute to the field-like torque. And I don't know if in your calculation you have this the other type of antidenting. Why do we have it, and what's the origin of this antidenting contribution?
I mean, I know how to do a calculation that will satisfy you, that will give only one of the two, but I'm not sure that it is correct. So all I'm trying to say is that if we do the calculations like this with the Boltzmann equation, which clearly neglects certain interference effects, right? Classical, then both torques appear. I think that's very intuitive, because there is a torque that of course tilts the spin towards the magnetization, but then so in the end, the spin, if you remember my animation, it keeps precessing about the magnetization, so the torque will naturally have both components. I don't know if this is convincing either.
But that should be averaged out if you.
Yeah, it averages to zero, but since it is decay, right? As you propagate, there is a kind of interference between K up and K down. So So it averages to 0, but when you integrate over space, I have some results, for those talks, which show really how they are both present in this method. Simply go like this. Okay, so this is what we got, right? So the two components of the torque, right? Perpendicular and parallel. And so near the surface, one of the two is much smaller than the other. And then, there are all these space oscillations, but both of them actually, so these are the spin currents. When you integrate, you end up with, in fact, the torque is just the value of the spin current at the surface. You see, it's different from 0 in both cases. So I don't, but on the other hand, it is possible to do calculation fully quantum mechanical with all the interference, in which one of these two, I don't remember now which one.
I think, actually, to do calculation, we can get both torques, but I think the other contribution, any damping or damping-like torque, actually from this interband transition or vary-phase contribution, if you like, in the other kind of language. So, well, we can talk about this later.
Both are observed, however, right?
Yeah, sure, of course.
So we are happy to see that they were both coming out.
But I don't see why from this inverse Einstein fact you can get this damping-like torque. But anyway.
Yeah, right, it's not only